Welcome to 114th Theoretical Physics Colloquium by Professor Irene Tamborra from Niels Bohr Institute. She received her PhD from the University of Bari in 2011. Then she had Alexander von Humboldt Fellowship at Max Planck Institute of Physics in Munich between 2011 and 13. She was at the Center for Excellence at the University of Amsterdam between 2014-15, and she became an assistant professor at Niels Bohr Institute in 2016. In 2017, she became Mercator Fellow for the Collaborative Research Center in Germany at Max Planck Institute for Physics and Astrophysics. Since 2021, she is a full professor of particle astrophysics at Niels Bohr Institute. Over the years, she received some important awards like Carlsberg Distinguished Associate Professor in 2019, Mirac Prize from the European Astronomical Society for pioneering contributions to understanding the role of neutrinos in astronomy and astrophysics, Shakti de Gaulle Award in 2019, and KIF Prize from Danish Network for Women in Physics in 2020. Her research interests are particle astrophysics, neutrino astrophysics and cosmology, multi-messenger astronomy, core collapse supernovae, complex binary mergers, and many other aspects of astrophysics. And today she will be talking about probing the cosmic unknowns through neutrinos. And with that, I'll give the microphone to Irene.
Thank you very much, Igor, for the invitation, and also thank you everyone for being here. So indeed, I am going to overview a little bit what we can learn about mostly extreme astrophysical events by using neutrinos, and I will put them within a multi-messenger context. So to begin with, we can think about the fact that in order to learn about the universe over the past centuries, we have been using our senses. That is, of course, what we do whenever we want to explore the unknown. And of course, in this sense, what we have been doing is to use our sight. And this is how we started in the past centuries ago to explore the cosmos. And then we have gradually broadened towards other wave bands. And indeed, in the 90s, Russell and Turner put together the grand unified photon spectrum that gathers all the information that we have about the universe in photons across wave bands. Now, today we are in a very different situation in that we can actually use other senses to explore the universe. And by senses here, I mean, of course, messengers. So besides photons, we have also neutrinos, gravitational waves, cosmic rays. And indeed, we here you can see a collection of all the information that we have about the universe in these different messengers. And of course, with the gravitational waves, we are right now starting to explore. So many of these things are still not detected, but we are getting there in the near future. So in my talk, I will first give you an overview of the current status of multi-messenger astronomy, and then we will dive into compact astrophysical sources and the cosmic accelerators before I conclude. Now, the first source that I would define as a source that has been observed with more than one messenger is, of course, our sun. Of course, we can observe our sun with the naked eye, and today we also observe it with the gamma rays and are studying the external regions of the sun. And for those of you that are not expert of neutrinos, the image that you see here is an image that was taken by the Super Kamiokande collaboration through neutrinos. So while we usually are not used to actually look at the sun in these terms, because we don't see neutrinos, by relying on the elastic scattering of neutrinos on electrons, which is a kind of scattering that preserves the directionality of the incoming event, the Super Kamiokande collaboration has been able to reconstruct this image. Now, the detection of neutrinos from the sun has been crucial to test the standard solar model, but also has triggered then studies in neutrino physics that led to the discovery of neutrino oscillations. Besides, of course, we probe also the solar model by using photons. Then in 1987, we detected the supernova in 1987 in the Large Magellanic Cloud, and this is up to now the only supernova that we have detected both in photons as well as neutrinos. A core collapse supernova originates from the death of a star whose mass is at least 8 times heavier than our Sun, and all the energy basically goes into neutrinos. Indeed, we expect 10 to the 58 neutrinos being emitted during the explosion. At that time, we only detected a bunch of them because we had less detectors than we do today, and many of them were also not working. And despite the small statistics with respect to current perspectives, this detection was actually extremely useful because it was the first proof of the first test of the core collapse physics. And also even now, after more than 30 years, we still use this event to actually place constraints on physics beyond the standard model. What you see here is an image of the remnant of this supernova, which has been obtained by overlaying different wave bands on top of each other. And then more recently, since 2013, we started to observe the high-energy neutrino sky through the IceCube Neutrino Observatory at the South Pole. And here we see neutrinos that have astrophysical origin. And while we don't know for many of them their origin, we know and we are currently observing possible connections between neutrinos and some astrophysical events. And so some of them, for example, seem to be linked to starburst galaxies, others to blazars that are a special kind of active galactic nuclei, and others to tidal disruption events that occur when a star is ripped apart by a black hole. So while, as I mentioned, there are still many things to learn about these sources, we are being pushed at the moment towards improving our understanding of the particle acceleration theory that, of course, is needed to model the signals that we see. And also, we need to improve our understanding of how these sources are actually working. And although it didn't include the detection of neutrinos, in 2017, we also detected the gravitational waves together with the photons resulting from the mergers of two neutron stars. And we also observed, of course, besides the merger itself, also the kilonova that comes from the radioactive decay of the heavy elements that we generate during the merger, as well as the short GRBs. And so through this multi-messenger detection, we have then started to get the first observational hints of the sites where the elements heavier than iron could be formed. So what is then coming next? In one of the when we think about exploring the cosmos by using particles, of course, neutrinos play a very special role. And the reason is that they exist in 3 different kinds, nu, nu mu, and nu tau. And of course, then we have their own antiparticles. And they are extremely weakly interacting. And this means that if we want to use them as probes of astrophysical sources, this is actually a perfect quality because they carry information that is not lost along the way. Moreover, they are the second most abundant particles in our universe after photons. And of course, the price that we have to pay is that these particles are also elusive. So it's actually difficult to detect them. And this is why we needed to build very big detectors so that the effective cross-section is actually larger. And then we have a higher probability of catching them. And so if we compare them to other messengers, then both neutrinos and gravitational waves are the only ones that are produced deep in the core of the sources. And so, as we will see in a moment, they carry crucial information about the most extreme conditions that occur in the core of the sources that we cannot probe otherwise, because photons, of course, won't survive. While if we consider, for example, cosmic rays or protons, they will be produced, of course, in the outskirts of the source, and then the trajectories will be bended because of effects of magnetic fields. And similarly, photons interact very often, and so we lose information on the way. So in this sense, if we think of doing astrophysics, of course, neutrinos are really ideal candidates despite their weakly interacting nature. Now, in this sense, then we can reconstruct, in principle, the energy distribution that we will see with the neutrinos from a certain source, and we can do the same also for photons. We can reconstruct the evolution of the neutrino signal as a function of time. And additionally, given that we have the three flavors, we can exploit the flavor ratio to get additional information about the physics that is ongoing in the source. This is something quite peculiar of these particles, while of course we can reconstruct the other two also for photons. Of course, we can consider polarization in the context of photons, but for neutrinos, we can really study also neutrino physics by using the flavor. So the idea of using them to do astrophysics is actually something that has been a dream for a long time. Indeed, in the 30s, Bethe and Peirce were saying that we can conclude that unless there are no new forces, there is practically no possible way of observing the neutrinos. And then John Bacall, which has been a pioneer in this field, was starting to understand in the 60s the importance of using neutrinos to study astrophysics. But he was also aware of the challenges intrinsic to this problem. And indeed, he wrote that neutrinos with their extremely small cross-sections can enable us to see into the interior of a star. But in the preface to his book at the end of the 80s that was titled Neutrino Astrophysics, he wrote that the title is more of an expression of hope than a description of the book context. And the observational horizon of neutrino astrophysics may grow, perhaps in a time as short as 1 or 2 decades. And indeed, this is actually what happened. Despite those challenges, right now we are in a very different situation where we can actually take advantage of these particles and learn about sources as well as the physics of neutrinos themselves. So I showed you already before this plot. This is what we call the grand unified neutrino spectrum in analogy to the grand unified photon spectrum that I showed also at the beginning of my talk. And here you can see all the information that we have today about the universe in neutrinos. And so you can see as neutrinos are spanning a very broad energy range, and also in amplitude of the flux, we have over 48 orders of magnitude. Of course, we have neutrinos here coming from different source classes, and in the remaining part of my talk, I'm going to focus on this region here, and I won't cover the region to the left of this talk, but if you want, we can discuss about it later. Now, in terms of detecting those particles, here you see a summary of the detectors that we currently have available around the world. And the ones that you see in parentheses are currently under construction or they are being planned. Probably I'm missing some of them because this is an extremely active area with a lot of new proposals. But what is interesting is that most of these detectors are actually using different technologies, and they are also sensitive to different flavors. And this means that we can combine the information that comes from different detectors by observing one single source, which of course provides complementary information concerning the sources. Additionally, we have also been exploring alternative technologies to do neutrino astrophysics. And one which I find especially interesting is the coherent scattering of neutrinos on nuclei. So in this context, we already have direct detection dark matter experiments, like, for example, the xenon experiment, whose successor will be Darwin, and similarly, dark side and Argo. And in this case, we can basically use already these detectors to do neutrino astrophysics. And the reason why this is interesting is that if we consider the coherent scattering of neutrinos on nuclei, this is flavor insensitive, while the detectors that I showed you in the previous slides are all mainly sensitive to one specific flavor. So given the uncertainties that might come, for example, from our understanding of flavor oscillations, by relying on these detectors, we have alternative and complementary information to the one with respect to the one that we get from traditional neutrino telescopes. And moreover, those are kind of compact experiments, which of course will allow us to get smaller statistics than the traditional ones, but is still very useful. And more recently, we also proposed the ResNova detector to be installed at the Gran Sasso laboratories in Italy, which relies on the same principle, although is actually a dedicated neutrino astrophysics telescope, and does as active material lead instead of xenon of argon. And the reason is that by using actually archaeological lead, we have a larger cross-section than we do with xenon, so we managed to get even a better event rate than the dark matter detectors. So then we move on to the sources with the, like the detectors and all the landscape that I just described, something that I find very interesting and where still we have a lot of open questions are compact astrophysical sources. And the first that I want to consider are core collapse supernovae. So we mentioned that we already detected in 1987A a supernova in neutrinos. And then the question is, what is coming next? So when we will detect the next supernova, hopefully close to our galaxy, then if the supernova is very close by, so a few kiloparsecs, we could detect the pre-supernova neutrinos, on which also Cecilia has been working, where we expect to see basically these neutrinos from the latest stages of burning of the star that is about to go supernova. And then we will see a burst of neutrino events that is coming from the core collapse, and together we will also see gravitational waves. And only a few hours up to 1 day later, we will see the shock breakout in photons and then the electromagnetic light curve. So the neutrinos then will be emitted early enough that they can be used to actually alert astronomers that a supernova is going off, because of course by interacting weakly they don't spend a lot of time before to leave the star. Now, one of the things that we can probe with the neutrinos is the core collapse mechanism. Indeed, today we don't know yet for sure how a supernova explodes, but we think that most supernovae are powered through neutrinos, which means that we form a shock wave in the iron core, and then it loses energy by dissociating iron nuclei, and the neutrinos then provide new energy to the shock wave to revive it and then trigger the explosion. While this process is taking place, there are hydrodynamical instabilities that make the energy transfer between the neutrinos and the medium more efficient, like, for example, convective motions or the standing accretion shock instability that is sloshing or spiral motions of matter that is tracked by neutrinos. And here I'm showing you some snapshots of a three-dimensional hydrodynamical simulation, where you can see that we start from a spherically symmetric object. This is the protoneutron star, and those are isocontours of entropy. This is the shock wave. And then as we evolve in time, we started to develop large-scale asymmetries and those plumes that are due to convection and also to SASI. And here you can see that in the event rate that we expect to see as a function of time, for example, with the IceCube detector, we would see large amplitude modulations of the neutrino signal that are actually tracking these sloshy motions that we see in the star that are taking place. And the same is true also for gravitational waves. So basically, by detecting both gravitational waves as well as neutrinos, we would be able to probe these conjectures about how a supernova is exploding and which is the physics that is going on just before the explosion. Similarly, we also showed that we know that not all supernovae can actually lead to the formation of a proto-neutron star, because in some cases we could have black hole forming collapses. And right now we have, at least from theory, evidence that we could have also a large fraction of black hole forming collapses in the when a massive star collapses. And so here, in this case, these sloshy motions are actually, and the SASI activity in general is actually extremely strong. Here you see the neutrino signal, and you see that this signal is actually chopped at the moment of black hole formation. So we can, if we see neutrinos from this kind of stellar collapses, then this is a very clear signature that actually we are forming a black hole. Additionally, what you see here is the spectrogram of the neutrino signal, and you can see this is the typical frequency of the signal. And you can see that this red region here is going down and then up and then down again. And this is happening because the typical frequency of these modulations is linked to the shock radius evolution. So what we see here is the shock radius that is contracting and then expanding and then contracting again just before the black hole forms. So by looking at neutrinos and similarly also gravitational waves, then we can explore the physics that is ongoing just before the formation of a black hole that otherwise we have no ways to see or to probe. As I mentioned before, the neutrinos can be used also as an alert system, and indeed we have in place the so-called supernova early warning system, or SNEWS, that is a network which has recently been rebooted as SNEWS 2.0, that is a network among neutrino detectors everywhere in the world that will release an alert as soon as a supernova will go off. And this is useful because then we can inform astronomers as well as gravitational wave physicists that there is a burst, and they have enough time to actually orient their telescopes and then catch the shock breakout in photons. But also it could be crucial because we have, as I mentioned before, some supernovae that could actually fail and so lead to formation of a black hole, or they could occur in very dusty regions, so they would be difficult to detect. And so by using neutrinos, we have then an alternative way to then catch those collapses and actually understand how many of them we have in the sky. And exactly by relying on the same principle that I showed you before for the solar neutrinos and the picture of the solar neutrinos, we can use the neutrinos from a supernova to point in the direction in which the supernova is going off. And right now we can predict, I mean, with the upcoming detectors, we will reach sub-degree precision in the localization, which is comparable with what we can do now also in the optical waveband. So it's quite interesting. Now, another aspect that is quite interesting is that up to now I have been focusing on the detection of neutrinos coming from a single burst, but of course we expect, for example, in our galaxy 2 or 3 supernovae per century. Yet we can also have supernova exploding elsewhere in the universe, and in fact one supernova is exploding every second somewhere in the universe. So we can detect the diffuse supernova neutrino background, which is the background of all neutrinos that are coming from all supernova exploding somewhere in the universe. This is a steady and guaranteed signal which we predict. However, we have not detected it yet. And what you see here, those gray lines are theoretical models, and here you see the most recent data that we have from the Super Kamiokande and CAMLAD collaborations. And so you can see that already some of the most optimistic theoretical models have been excluded, and these are extremely exciting times in this context because we are currently enriching the Super Kamiokande detector with gadolinium, exactly with the purpose of improving the signal over noise ratio and then actually move towards the detection of this signal. And also Juno, which is a liquid scintillator, is being built in China, again by having the detection of the diffuse supernova neutrino background as one of the main purposes. So this is very exciting, and within the next 2 or 3 years, probably we will have the first data about the DSMB. And the reason why this is interesting is because it will push low energy neutrino astronomy towards cosmic scales. And also we can use this signal to start to learn about the rate of supernova and about the rate of black hole forming collapses by using neutrinos. Now, while this happens on the theory side, we also have a lot of work to do, especially for what concerns the uncertainties that we have in the modeling. One of them being the supernova rate, the other being the effect of binaries that in which, for example, those supernovae could occur that would also modify the signal that we expect to see, and many others. Now, another aspect that is also something that we should consider is the fact that the neutrinos can change their flavor. And so while what I mentioned up to now, it's of course is sensitive to the flavor, but it can anyway be probably disentangled. It's important actually to worry about what the neutrinos are doing in the core of a supernova. And in this context, we know that they will interact with the matter background, and this leads to the well-known MSW effects, where when neutrinos propagate in matter, we have an enhanced probability of neutrinos changing their flavor. However, as I mentioned in the beginning, supernovae are among the richest environments in neutrinos that we have in our universe, together with the compact binary mergers and the early universe. And this implies that the coherent forward scattering of neutrinos onto each other becomes actually relevant. Now, it becomes relevant in the sense that this is affecting the way the flavor is evolving, because we have a feedback of the neutrino field onto itself that otherwise in other contexts would have been negligible. So the big picture here is summarized in this plot, where this is the protoneutron star, and then the neutrinos will start to propagate, and this is the shock radius, and then those are the outer regions. So until a few years ago, we thought that the flavor oscillations were actually occurring in this external region here, which meant that, of course, they were relevant for the detection of the neutrinos, maybe also for the nucleosynthesis, but mostly like in this region here, where all the physics linked to the explosion is taking place, they were not considered. And this also kind of justified the fact that we can consider hydrodynamical simulations by treating neutrinos as radiation, so without taking into account the fact that neutrinos can change their flavor. However, more recent work has actually led to evidence that probably those neutrino-neutrino scattering gives rise to flavor conversions in this innermost region, actually even before neutrinos decouple. And if this is the case, then the question is, does this have an impact on the physics of the supernova itself? Because of course it can affect the explosion beyond affecting also the nucleosynthesis. And so it could somehow affect our current understanding of what is the explosion mechanism that I explained before. So together with my team, we have been then recently working in this direction, trying to understand within simplified models whether indeed this is actually something dangerous that we should be worried about. And what you see here are the angular distributions of neutrinos, because this effect is not only dependent on the energy, but also on the angle at which neutrinos are propagating, because the angle between the momenta of the neutrinos that are scattering actually affects this kind of conversion. And here you see in the, of course, in the innermost regions, the distributions are isotropic. And as we move forward in radius, then the distributions starts to become forward peaked. And what you see on the right is a plot of the abundance of the neutrinos as a function of radius. And here you see the decoupling surfaces. So what is going on is that the dashed lines are the ones that we take into account when no flavor conversion is included. However, when we take into account the fact that there are those neutrino-neutrino interactions that have an effect on the flavor evolution, then we change the location of the decoupling surfaces of neutrinos. Of course, this is a simplified model, but is the first of its kind that takes into account the advection of neutrinos, the collisions, and how all of this combines with the flavor evolution. And while we need to work more on this kind of problem, of course, it seems that indeed we can affect through neutrino physics the physics occurring at nuclear densities. And this is something that, yes, on which we should devote more work. And of course, it can have also implications on multi-messenger observations of those objects. Now, besides the neutrinos of lower energies, so the neutrinos produced thermally that I have been discussing up to now, we can also produce non-thermal neutrinos through particle acceleration. And in this case, we would basically have relativistic protons that would interact with the cold protons of the circumstellar medium surrounding the supernovae and generating, therefore, both neutrinos and gamma rays. And so we have, of course, different kinds of supernovae. And here you see a summary plot of the detection horizon of this kind of high energy particles coming from the different supernova types. What you can see is that with the CTA and also Fermi, we will be able to detect supernovae of type 2n and 2p, which are the supernovae that have a very kind of dense circumstellar medium. And we have a similar horizon also for neutrinos that will be within a detection reach with IceCube generation 2, as well as KM3net. And this is very exciting because we don't know a lot about the exact structure and properties of the circumstellar medium. And this offers somehow a way to actually probe the structure and the features of the circumstellar medium by using neutrinos as well as gamma rays. Okay, I'm going also to high energy particles here, and then we can stop in case you have questions just for the next couple of minutes, because of course some of these supernovae could actually rotate, and in some cases we can also harbor a jet. And so this would give rise then to what we know as a gamma ray burst, which would emit again particles of higher energies. And in this context, of course, gamma-ray burst neutrinos emitted from gamma-ray bursts have been subject of searches since a very long time. And here, indeed, you see the current experimental sensitivities and upper limits that we have from these sources. And we know by now that less than 1% of the diffuse background of neutrinos that we see from IceCube is actually coming from these sources. So we know that they are not the main contributors, yet we have the chance of actually detecting them as single sources in coincidence with neutrinos. And so in this plot that related to recent work led by Tetiana Pitik, we actually estimated the emission of neutrinos that is expected by having different mechanisms that are powering the jets of gamma-ray bursts. Indeed, we don't know exactly which is the mechanism that is powering the radiation of the jet that we see. And while in the electromagnetic radiation, we can roughly get to the same spectral energy distribution adopting different mechanisms, here you can see as there is a strong sensitivity of the neutrino signal to whether we consider that there is, for example, dissipation below the photosphere, whether we have internal shock models or magnetic dissipation in the jet and so on. And we can have variations of up to 1 order of magnitude in amplitude and a large shift in energy where the flux is peaking. And this implies that, of course, the detection of neutrinos from these sources would be great because we would have hints about the mechanism powering a gamma-ray burst, but also that we needed to be careful when we search for neutrinos from these sources because they, according to the mechanism, they could be sitting actually in different regions of the energy spectrum. Now, another interesting aspect is that for a long time we have been thinking that there are also neutrinos that are produced from below the photosphere, and they should be, and for example, we have been thinking that actually they could make the low energy region of the diffuse flux that we observe from IceCube because we cannot connect that part of the flux to gamma rays. And recently in a work led by Ercilia Guarini, what we did was to actually model the production of particles by relying on state-of-the-art collapsar jets simulations that include, of course, MHD effects. And there we found that there is a strong mixing between the cocoon that collimates the jet and the jet itself. And this somehow makes the particle acceleration process less efficient because we have a jet that is heavily loaded with baryons. And therefore, we predict as a result a flux of neutrinos, which actually sits really at the same, in the same energy range as the atmospheric neutrino flux. And this is the prompt emission that I showed you just before, so from above the photosphere. And so there is, in this sense, a difference with respect to what was predicted in the past through simplified models that were not considering these strong interactions between the cocoon and the jet, and therefore were predicting neutrinos in a higher energy region than in the past. And so somehow this hints that we really needed to move forward towards a more self-consistent modeling of the production of these particles in the sources, given that we have data and we needed to understand from where these neutrinos are being originated. Yes, so the next thing I wanted to mention are compact binary mergers, which are coming from the merger of two neutron stars or a neutron star and a black hole. And those are similarly rich environments in neutrinos. And you can see here that we have a very multi-messenger source also in this context, in the sense that we will detect gravitational waves, and then we expect to see a short gamma ray burst with possibly neutrinos as well, and then we have the emission from the kilonova as well. and of course also cosmic rays. And so one thing, of course, in this context, we cannot expect to see neutrinos from a single source as we would do for a supernova, because we don't have many mergers expected to happen close by. However, neutrinos play an important role indirectly. In fact, together with the supernovae, we think compact binary mergers are the sites where the elements heavier than iron could originate. And in fact, from the kilonova 2017, we have had some hints that indeed this could be the case, at least for a fraction of these heavy elements. Now, in this context, the element formation is actually driven by beta reactions. And so you can see here that we needed to know then which is the fraction of electroneutrinos and antineutrinos, because this would affect the fraction of protons and neutrons that we have in the end. So in order to generate elements heavier than iron, we needed to have a neutron-rich environment to enable the rapid neutron capture process. And this implies that if, for example, because of oscillations, we change the fraction of electron antineutrinos versus neutrinos, we can change the proton over neutron ratio. So we started to worry about this a few years ago in my group, and we tried to understand what could actually be the impact that this then would eventually have on the electromagnetic observations. And more recently, in a work led by Oliver Just, we ran a self-consistent hydrodynamical simulation where, in a parameterized form, we included the conversion of the flavor conversion of neutrinos. And this had as a result the fact that we actually impacted the cooling of the disk, but also we can affect the synthesis of the elements, especially of lanthanides, by a factor of 2 or 3, which has then an effect on the kilonova emission. So, of course, more work is needed in this direction, especially in terms of exploring the population of mergers that we expect to see and see how this impacted then the electromagnetic observables. But certainly this is something else that we need to take care of when we make predictions for future and upcoming kilonova observations. Moreover, we expect, as I mentioned, as a result of the compact binary merger, we can have also a short gamma ray burst, which we have observed, for example, in 2017. And in that case, we could emit neutrinos similarly to what I mentioned for long GRBs, but for the 2017 event, we have not observed any of them. And this is totally in line with expectations. Indeed, here you see the upper limits placed by the various experiments. And here you see a bunch of theoretical predictions. And the reason why we didn't see any neutrinos was that in this case, the jet was actually slightly off axis with respect to us. And so if, for example, we see future events of this kind and the jet happens to be on axis, then we have good chances to actually detect those neutrinos. In particular, if we see them at very high energies, then this could be indication, together with the gravitational waves, of the existence of a long-lived magnetars. And so there are very encouraging prospects of detecting these objects in multi-messengers in the future. Now, moving again to higher energies, then there is a range of cosmic accelerators that leave a lot of questions open. So, of course, some of them I already mentioned, like high energy emission from supernovae or gamma ray burst. But I mentioned in the introduction that we are observing links of neutrinos with several other objects, like star-forming galaxies, tidal disruption events, and so on. And this is quite interesting. Indeed, like here, you can see a plot of the number of alerts that was released by the IceCube collaboration as a function of time. And you can see that the number of alerts released in the past few years has been increasing very much. And so we have a lot of follow-up programs right now, both of electromagnetic surveys that rely on neutrino alerts as well as vice versa. And so this is getting exciting because we have a real chance to actually learn about bright transients that occur in the local universe. So among those, I find interesting the possible detection of neutrinos in coincidence with the tidal disruption events, which, as I mentioned, occur when a star is ripped apart by a black hole. And in this case, we have observed for 3 of those events neutrinos in coincidence with the observations coming from the Zwicky Transient Facility. And we observed, strangely enough, all these neutrinos actually about a year after the peak that was reached electromagnetically. Those were very bright events with a large bolometric flux and a copious UV and optical emission. For none of them we have seen a jet. And the question then is, how do we actually make these neutrinos? And so there have been a lot of scenarios proposed. We could make them in a jet that eventually could be choked, or we could make them in the accretion disk or in the wind. Somehow we can reach conditions that are consistent with the production of one of these high energy neutrinos. In my opinion, it's kind of interesting that then we would have an emission that is so delayed in time. And also there have been papers recently claiming that actually those neutrinos are not coming from tidal disruptions, but those are rather coming from blazars that are located in the same source. So we are actually seeing neutrinos from elsewhere. So the regions where we could have efficient particle acceleration in these sources then remain to be assessed. But recently we considered actually one of these sources, which was a TDE observed, one of these 3 that I mentioned before, that was observed to occur in a narrow line Seyfert galaxy. And by looking at the light curve, also together with our observer's colleague in a work led by Tetiana Petic, we concluded that this is actually a hydrogen-rich superluminous supernova rather than a tidal disruption event. And this was coming from the fact that the light curve tends to flatten up. And in a sense, this would actually make the neutrino production a little bit more natural besides the electromagnetic characterization. Because in the neutrino signal, then we would expect a constant probability of seeing neutrinos as a function of time after we actually reach the peak in the neutrino signal, which then would explain why we see them so late. And so, of course, the jury is still open. We don't have a clear answer, but we should keep an eye on the fact that we are observing a growing number of transients, and for some of them, there could be also misidentifications that then, of course, could affect our multi-messenger interpretation of the sources. Now, another thing which is interesting is also that we are discovering new classes of transients. And so here you see a summary of currently known transients. And here there is this class which is relatively new that are fast blue optical transients. So those have been discovered a few years ago, and they were originally exchanged for supernovae. And they are peculiar because they have an extremely fast rise time, and we think, but however, here you see a comparison with supernova, then they kind of differ, and we know today that they are powered by a compact object that then is launching an asymmetric outflow. So we observe a few of them today, and we have been trying to understand what is actually powering these sources. And for example, there are two scenarios that seem to work, which could be either that we have a massive star that possibly has not been completely stripped of hydrogen, that launches a jet that then is choked in the envelope. Or we could have a model where we have a Wolf-Rayet star that enters in a common envelope phase with a black hole. And in both cases, we would manage to obtain a circumstellar medium which is asymmetric, which then is compatible with observations. And now, if we model the neutrino prediction from these cases, then we could see actually a different neutrino signal according to the mechanism that is powering the source, which again would be degenerate in the context of electromagnetic emission, at least for what we know now, which is just preliminary knowledge. And so it's interesting also because actually we already have upper limits for one of these events in neutrinos, and we seem to have a good detection chances as we observe more of these fast blue optical transients to then keep an eye also on their possible emission of neutrinos. And at the same time, by using those high energy sources, even if we don't know from where the neutrinos that we see are coming from, we are still already able to actually use this data to constrain the properties of the sources. And so, for example, in this plot that you see here in a work that we did with Mauricio Bustamante, we tried to constrain the amount of magnetic field that is harbored on average on the sources that we see from IceCube, which of course at the moment is excluding extreme scenarios like magnetars, but this is going to get better in the future. And similarly, we can constrain also the evolution, the redshift evolution of the sources that are making the neutrinos that we observe at the highest energies. So this brings me to my conclusions. We currently are in an era where we can exploit fully synergies among different messengers. We are just starting to model a little bit better the physics of the microphysics of the sources. And at the same time, we are discovering unique opportunities to learn more about the sources, the physics of the particles themselves, as well as we could use those sources as a gateway to learn about BSM physics, which I didn't touch in this talk. And all of this is happening while we have an exciting range of new telescopes coming online that will just make us ready for new discoveries. Thank you.